Welcome, everyone. Thank you for joining us today for this exploration into architectural modernization. As we look at the landscape of enterprise technology, one of the most significant challenges remains the transition of legacy Cobol systems into modern environments. This slide serves as a high-level roadmap for that journey. Starting on the left, we represent the foundation, the legacy Cobol applications that have powered core business logic for decades. To move these into the future, we focus on two primary modernization strategies. The upper path illustrates the Java route, utilizing Cobol to Java conversion tools. This path leverages Java's vast ecosystem, enterprise-grade stability, and deep pool of developer talent. Conversely, the lower path highlights the Go route via Cobol to Go. This approach is increasingly popular for its superior runtime efficiency, high-performance concurrency, and seamless fit within cloud-native and containerized infrastructures. Ultimately, both paths aim to land in the modern cloud architecture, visualized on the right. Throughout this presentation, we will provide a comparative analysis of these two strategies, focusing on porting efficiency, runtime performance, and long-term industry viability.
Java offers stability for logic preservation, while Go provides exceptional efficiency for cloud-scale operations. When evaluating porting architecture, Java's object-oriented nature aligns naturally with the verbosity of Cobol, which facilitates a safer and more automated transition. In contrast, moving to Go often necessitates structural flattening and complex manual re-architecting. From a cloud ROI perspective, Go is the clear leader in resource efficiency. It delivers startup times up to 100 times faster and reduces cloud infrastructure costs by 80%, making it the optimal choice for serverless environments and high-density Kubernetes clusters. Finally, we must consider the maturity gap between these two paths. Mature automated translation tools, such as Blue Age and Astadia, are already well established for Java. Go currently lacks these off-the-shelf conversion tools, which means adopting Go typically requires a comprehensive rewrite strategy rather than a standard migration strategy.
The central challenge in modernizing legacy systems is often described as mapping the unmappable. Cobol's reliance on fixed precision arithmetic, specifically the PIC9 format, and its use of one-based indexing creates a significant architectural gap when moving to modern environments that favor dynamic primitives. As shown in this mapping table, we have defined how Cobol source types translate into Java and Go targets. For numeric fields with 1 to 9 digits, we map to a 32-bit integer in Java and a platform-dependent integer in Go. For larger fields of 10 to 18 digits, we utilize 64-bit representations, long for Java and int64 for Go. Decimal values defined with PIC-V are mapped to double and float 64, while alphanumeric strings map directly to native string types. Crucially, we must consider the architectural note regarding performance versus precision. While primitives are currently used to maximize speed, production financial systems require more robust custom implementations, such as big.java in Java or big.rad in Go. This transition is essential to eliminate floating point errors and maintain the rigorous precision required for financial data integrity. When modernizing legacy systems, structural friction arises from how different languages handle data arrays and logic flow. One of the most common issues is the indexing gap. Cobol uses one-based indexing, while modern languages like Java and Go are zero-indexed. To maintain traceability to the original source, generated code must use explicit index-1 arithmetic. This ensures that business logic remains consistent even as the underlying memory addressing changes. Another significant challenge is structure flattening. Cobol often utilizes nested occurs groups to represent hierarchical data. During modernization, these nested groups are typically flattened into parallel arrays. For instance, a Cobol record like WS Student occurs 3, containing both names and grades, would be split into two separate arrays in Java or Go, one for the student names and another for their grades. This approach simplifies data access in the modern environment while ensuring the integrity of the original data relationships. This slide illustrates the paradigm shift between object-oriented and structural programming through a comparison of Java and Go. On the left, we see a traditional Java implementation. Java follows a verbose class structure, where every piece of logic must be encapsulated within a class. It requires strict attention to null safety and relies heavily on exception-based error handling. In contrast, the Go implementation on the right demonstrates a more concise, package-based structure. Go utilizes the concept of zero values to mitigate null pointer issues and favors explicit return-based error handling over exceptions. Ultimately, while Java remains conceptually closer to original Cobol logic, Go offers a more maintainable ecosystem by eliminating deployment complexities such as jar hell. When examining the relationship between runtimes and cloud efficiency, we see a massive performance gap between Java and Go. Starting with startup time, Go is 100 times faster, initializing in a mere 50 milliseconds compared to 10,000 milliseconds for a typical Java application. This speed is a primary driver for system responsiveness and agility. In this ROI analysis, we examine the cost implications of running 100 replicas on AWS EKS. Our legacy Java infrastructure requires 50 vCPUs and 100 gigabytes of RAM. This high resource demand leads to lower bin packing density and a monthly cost of approximately $3,600. In contrast, modern Go infrastructure is far more efficient, requiring only 10 vCPUs and 12.5 gigabytes of RAM. This significant reduction in overhead facilitates high bin packing density, lowering the monthly cost to approximately $720. Overall, this transition represents an 80% cost reduction, showcasing the clear economic benefits of modernizing our stack. When evaluating the choice between Java and Go, we must consider the human factor, specifically how each ecosystem influences maintainability and staffing. Java's primary strengths are rooted in its maturity. With roughly 35% market penetration, it offers an unparalleled talent pool, making it significantly easier to staff a project. This is supported by a robust tooling ecosystem, featuring industry standards like Visual VM and SonarQube, as well as over 30 years of proven backward compatibility. On the other hand, Go excels in operational simplicity and modern deployment needs. Its design allows for faster developer onboarding by avoiding complex abstractions, often referred to as magic. From a security perspective, Go minimizes the risk of supply chain attacks through its minimal dependency model. Furthermore, its fast, reproducible, and zero-dependency builds provide a streamlined experience for technical operations. Ultimately, the decision involves a clear trade-off. Go is designed to be easier to run and manage technically, whereas Java's massive ecosystem ensures it is easier to staff and scale from a human resource perspective.
The automated translation gap highlights a critical divergence in legacy migration strategies. When starting with Cobol source code, Path A offers a well-established route via automated translation. Using mature tools such as Stadia, Blue Age, or software mining, organizations see high success rates because these tools align well with Cobol's inherent verbosity. Conversely, Path B, what we call the Go gap, presents a significant hurdle. There are no mature, off-the-shelf translators for Go, forcing teams to rely on custom adapters. The root cause for this is that a direct, line-by-line translation results in unidiomatic code that contradicts Go's fundamental strength, particularly its concurrency model. Consequently, moving from Cobol to Go is rarely a straightforward conversion. It is fundamentally a complete rewrite. Let's examine the contrasting approaches to modernizing technology stacks through these case studies: migration versus innovation. On the left, we have the migrators, who operate with a safety-first mindset. Their primary objective is functional equivalence, ensuring the new environment performs exactly like the legacy system it replaces. For instance, ING Bank converted 1.5 million lines of code to Java, running the new system side by side with their existing mainframe to ensure a seamless transition. Similarly, Foyer Group utilized automation to move to Java, specifically to facilitate their exit from legacy hardware. In contrast, the innovators on the right prioritize scale first. Their goal is high concurrency and speed, often choosing to build from scratch rather than migrating old code. Monzo exemplifies this by building over 1,600 microservices in Go using a greenfield approach. American Express follows a similar strategy, leveraging Go to build entirely new payment networks instead of focusing on legacy porting. Ultimately, the choice depends on whether an organization needs to preserve existing business logic with precision or build a new foundation optimized for massive scale and performance. When modernizing legacy systems, we must address the critical risk of Jobol versus the benefits of intelligent refactoring. The primary problem with simple automated translation is that it risks creating Java syntax Cobol, often referred to as Jobol.
While this code may compile, it unfortunately retains the original legacy spaghetti logic, failing to deliver the true benefits of modernization. To mitigate this risk, we look toward three key solutions. First, logic extraction involves deconstructing complex business rules and rebuilding them within modern frameworks, an approach utilized by platforms like AWS BlueAge. Second, AI-assisted refactoring leverages generative AI, such as IBM watsonx, to explain existing code and incrementally refactor subroutines into a cleaner, more maintainable state. Finally, app understanding focuses on mapping logic dependencies before any rewriting begins, using tools like Swim or Sonar to ensure a comprehensive grasp of the system's architecture. By employing these intelligent strategies, we move beyond mere syntax translation to achieve genuine digital transformation. This strategic decision matrix provides a framework for choosing the right architectural path by weighing performance needs against risk tolerance. On the vertical axis, we measure performance requirements from standard to extreme, while the horizontal axis tracks risk tolerance from low to high. In the bottom left quadrant, we have Target Java, a lift and shift strategy. This is the optimal choice when risk tolerance is low and business logic preservation is the priority. It offers a stable, lower-risk migration path for standard performance needs. Moving to the top right, Target Go is recommended for organizations with high risk tolerance and extreme performance requirements. This greenfield or rewrite approach is designed for modern, cloud-native applications that demand maximum efficiency. Between these poles, we find niche optimization for high performance needs with low risk appetite, and hybrid architecture for those willing to take more risk to balance modern and legacy components. The fundamental choice often comes down to one key question. Are you trying to save the logic by staying with Java, or are you trying to save the infrastructure budget by migrating to Go? Our hybrid architecture proposal represents a best-of-both-worlds strategy designed to balance performance with stability. At the perimeter, we have the edge layer, built using Go. This layer is specifically engineered for speed to handle high-volume traffic, managing our APIs, routing, and high-concurrency microservices. To conclude our strategy overview, let's look at our final recommendations for modernization. First, for a lift and shift approach, the primary target should be Java. We suggest utilizing enterprise suites such as BlueAge or Astadia to minimize execution risk and ensure business logic is fully preserved. Second, when re-architecting your applications, the target language is Go. It is essential to avoid simple translators here. Instead, employ AI extraction techniques to define your core business rules and then rewrite them for optimal cloud-native performance. Third, a critical tooling warning. Exercise caution with POC converters in a production setting. Many lack the necessary support for CICS and DB2, and they frequently fall short on the precision handling required for financial transactions. The bottom line is simple. Java provides a reliable bridge to the present, while Go offers a high-performance foundation for the future. The research and findings presented today are grounded in a comprehensive set of references and data sources. Our technical framework for data consistency is informed by the latest architectural standards for Cobol to Java and Go type mapping. To evaluate the efficiency of the migration process, we utilized a comparative study of modern language converters, specifically focusing on the trade-offs between Java and Go as target environments. Our broader strategy draws from established industry literature on modernizing legacy Cobol architectures and migration methodologies. Furthermore, we have validated our approach against real-world implementations by examining case studies from leading global financial institutions such as ING, Monzo, and American Express. Finally, all cost-benefit analyses and performance projections are supported by current AWS EKS pricing data and cloud runtime benchmarks. These sources collectively provide the rigorous evidentiary basis for our modernization roadmap.